Today's lesson is on applications involving rational equations. So applications, we're going to be working with word problems. And using rational equations, that means that somehow there are going to be fractions involved, particularly fractions that have a variable in the denominator. I'm going to jump right in and start solving this. Remember, you can pause the video in order to take some time to write this down before jumping into the problem. Remember that I've been promoting in our class the use of a chart. The chart isn't actually necessary. It is simply a way of organizing our information. So I see that there are two situations in this problem about Jane rowing upstream and downstream. So I'm going to make one of my labels up and one of my labels down. When we've used this chart before, we've mentioned that it's very flexible and that depending on what you're working with, the amount, rate, and total can be slightly different. For instance, if you're talking about an investment, your rate would be a %. But in this case, your rate is a rate of speed. Your amount is going to be your amount of time, and your total is going to be your total distance in this particular case. So let's fill in what we have. Jane can row 4 miles per hour in still water. It takes her the same amount of time to row 8 miles upstream as 24 miles downstream. So total distance upstream is going to be 8 miles. Total distance downstream is going to be 24 miles. And that's because in that same amount of time, if she's going downstream, then the current is pushing her along. But if she's rowing upstream, then the current is pushing her back. Which brings us to the issue of rate. If she's able to row 4 miles per hour in still water, so water without a current, then when she's traveling upstream and the current is pushing against her, she's actually going to be going overall somewhat slower than 4 miles an hour. But as she's going downstream, the current is going to be pushing her along, adding to her rate of speed. So the rate is going to be 4 minus c for upstream and 4 plus c for downstream, where the current is pushing her along. The thing that's a little bit different about this problem than the other types of problems like this that we did earlier in this class is that normally we fill in these two columns in the middle, we multiply those to get the column at the back. But this time we have the column at the back filled in. Well, if this times this equals that, it must be that this divided by this is equal to that. Another way to look at this, up here, we're looking at distance, rate, and time. We have a formula that distance is equal to rate times time. But I'm trying to solve for time. I want to fill in this column for time. In order to do that, I would divide both sides by rate to isolate time, and I would find that time is equal to distance divided by rate. So you can think of it in either of those two ways that I've just mentioned. In order to represent this in our chart, we're going to grab the distance, divide it by the rate, and that gives us a statement for time. Distance divided by rate for upstream, distance divided by rate for downstream. Again, you do not have to use the chart. That's only a way of helping us organize our information and get what it is that we need to use. What we do need to do, though, is we need to find an equation in here. We need to find some things that are the same or that we can somehow set equal to each other. And what I'm finding here is that we do have the same amount of time. The same amount of time. Those two times are equal. So we're going to go ahead and set that up as our equation and work that out. So we have 8 over 4 minus c is equal to 24 over 4 plus, how about a c, not another 4. Because we have a single fraction on each side, we may cross multiply. So we end up with 8 times 4 plus c is equal to 24 times 4 minus c. So I'm going to go ahead and bring my work up here and see what we get from that. When we do the multiplication over on this side, we get 32, right? I'm distributing through. 32 plus 8c is equal to 24 times 4. That's going to give us 96. And then multiplying again, we get minus 24c. In order to solve this, let's add 24c to both sides. So this gives us 32 plus 32c is equal to 96. We'll subtract 32 from both sides. We get 32c is equal to 64. And in order to isolate c, which is what we're trying to solve for, how fast is the current? I use the variable c as a suggestive variable in order to remember I was talking about current. When we divide both sides by 32, we find that the answer is that c is equal to 2, which is what this fraction reduces to. And the units there are in miles per hour. The question is, how fast is the current? The current is 2 miles per hour. We've done many problems of this nature before. These are called mixture problems. They can have to do with distance, rate, time. They can have to do with investing money. They can have to do with being in a chemistry class and mixing 2 different concentrations of a saline solution. They can have to do with running a business where perhaps you're packaging boxes of chocolates where you've got milk chocolate at a certain cost and dark chocolate at a certain cost. All of those things are mixture problems. All of them can be done in a very similar sort of way. The main difference here is that instead of having the last column open and multiplying these two to get this, you will have one of these other 2 columns open, and you'll need to divide the last column by whatever you get here to fill in your empty column. So what we're going to do is go ahead and move on to a type of problem that you haven't seen before, and that is known as a work problem. I'm going to go ahead and erase all of this, but again, remember, you can pause at any time, you can back up this video at any time and rewatch something and take whatever time you need in order to get the information that you need. The problems I'm about to show you, known as work problems, can be solved using this chart also. You would put in the speed at which a person is working as being rate. The amount of time that the person worked would go right here. I actually find the chart to be a little bit confusing for this next kind of problem, so I'm going to show you a slightly different way for that I think just makes more sense. So what we're looking at now are called work problems. And they have to do with 2 or more people or 2 or more things, let's say printing presses or some other sort of equipment, working on the same job. And if we know how long each of them takes to do the job alone, how long does it take them to work together? So we're going to break this down a little bit. Let's say it takes my friend Bob 4 hours to mow his lawn. He's got quite a big yard, and when he gets out there to mow the lawn, it takes him 4 hours. So how much work has he accomplished if he has worked for 1 hour before he takes a break to go swimming or something? How much of the work has he done? What fraction of the work has he done? Well, if it takes him 4 hours to mow the whole thing, hasn't he done 1 out of the 4 hours, or 1/4 of the job or of the task? Well, what if he's worked for 2 hours? Isn't he halfway done because 2 is half of 4? Probably for our purposes, we want to think of it as he's worked for 2 out of the 4 hours, but we can make a little note that's in fact half of the job. And we could continue asking this question. Let's go ahead and do it. How about if he's worked for 3 hours? Well, he's almost done now. He's done 3/4 of the job. How long does it take him to complete the entire job? Well, it would take 4 hours, right? And if we keep this same structure of saying how long he worked over how long it takes him to finish the whole job, we would say that he's done 4/4 of the job. But can't we also reduce this and say 4/4 is equal to 1? And in this situation, that 1 means 1 full job, 1 completed task. So we are going to have fractions that have on the top how long the individual worked, whether that's a person or a copy machine or a printing press or a pipe that's filling a swimming pool, whatever is working, how long did that individual person or object work? And on the bottom, we're going to have how long it would take that individual to do the job alone. So that's what our fraction is composed of. How long the individual person or machine worked, and how long it would have taken them to do the job, the complete job all alone. And when we put this fraction in there, it gives us the portion or the fraction of the job that that person did. And what this is going to look like when we put it into an equation and try to solve problems with it is that we're going to have more than one person working on the job. So let's say that Bob's wife, Barbara, comes out and helps him to mow the lawn. Well, Bob and Barbara actually are both equally skilled at mowing the lawn, and they could both mow the lawn in 4 hours. Let's say Bob's been working for a while already. He got started first, and Barbara decided, hey, I want to help him. Well, it could be then that Bob has worked longer. He's already been working for a while. Barbara joins in. Oops. Or we could say Bob did 3/4 of the work and he got fed up with it and tired. He said, Barbara, you go take over for me. What remains to be done is 1/4 of the job. When we add those together, 3/4 plus 1/4, we get 1 or 1 complete job. So that's just a very, very basic example of the way this sort of thing works. How long this person, or in some problems it might be an object, a machine or a pipe or something that's working. One individual, another individual, when you add them up, they need to add up to 1 complete job. So let's look at some specific examples of problems that use this idea. Remember this structure here. If you need to pause the video at this point to write this piece down, please do so. So the first actual work problem that we're going to do together involves my sons when they were little. They are all grown up now, but Jacob and Caleb used to share a room. So we're going to say when Caleb and Jacob were little kids, they used to share a bedroom. Oops, bedroom. By himself, Caleb, who happens to be younger, could completely mess up the room, completely mess up the room in 20 minutes. It would take Jacob, who was older, 12 minutes to completely mess up the room. So then the question is, if they work together, how long will it take them to completely mess up the room? And again, I'm going to jump in and start talking about the problem. If you haven't caught up with me with your writing, hit pause and write the problem down. So if we had to make a guess on this, if we had to make an estimate, well, it takes Caleb 20 minutes. It takes Jacob 12 minutes. Often when people first come across a problem like this, they think, oh, well, it must be an average of their times. Halfway between 12 and 20 is 16, so maybe it's 16 minutes. But consider the following. If it only takes Jacob 12 minutes to do this job all by himself, but he has help, aren't we expecting that our answer is going to be less than 12 minutes? Because that's how fast the fastest messer-upper can do the job all by himself. So what we're going to do is structure this. I'm going to make a fraction for how much of the room Caleb messes up, and a fraction for how much of the room Jacob messes up. I'm going to add their two fractions together, and that should equal one entirely messed up room. So remember the structure we had over here earlier about what goes on top of the fraction and what goes on the bottom of the fraction. The question is, how long will it take them working together to completely mess up the room? I don't know how much time it's going to take them. That's my variable. But that's going to be how long each of them is working. They're working together. They started at the same time, and they're going to keep working until it's a total mess. On the bottom, we need how much time it would take each of them individually. Well, it takes Caleb 20 minutes all by himself, and it takes Jacob 12 minutes. If you're not sure where I did that, go back in the tape a little bit and look at what I wrote about Bob mowing his lawn and how much he got done in 1 hour. For instance, if these guys work for 10 minutes, didn't Caleb mess up half of the room? 10 minutes out of 20, which reduces to 1/2. So whatever time we put up here, that's finally going to give us our fraction of the room messed up by Caleb and the fraction messed up by Jacob, and they have to add up to 1. So this is a rational equation. We want to get rid of fractions here. So let's grab our LCD, the smallest thing that both 20 and 12 goes into. And the first thing that comes to mind for me there is 60. Both of those numbers will go into 60. Think about a clock. We are talking about minutes after all. If it helps you, put a 1 underneath the 60, since over here at least we are working with fractions. When you distribute through, 60 times t over 20 Well, your 20 goes into 60 3 times, so we have 3t. Plus, well, 12 goes into 60 5 times, right? I don't usually show my canceling, but this is what really happened. I multiplied 60 by t over 12. 12 goes into itself once, and into 60 5 times. 5 times t is 5t. Don't forget that you are multiplying both sides. So even though you don't see a fraction here, when you are working with an equation, if you multiply one side by something, you've got to multiply the other side by that same thing. Okay, so let's solve the problem. 3t plus 5t is 8t, which is equal to 60. We're going to divide and do some reducing to see what we can find out about this. So t is equal to 68. 4 goes into both of those numbers. 4 goes into 60 15 times and into 8 twice. And I'm talking about how long. I'm talking about an amount of time, and our units are in minutes. So maybe instead of that fraction, let's turn this into a mixed number or a decimal. This is the same as 7 1/2, or we could say 7.5 minutes. So the answer would be, working together, Jacob and Caleb can totally mess up the room in 7.5 minutes. And this answer should meet our expectations, because 7.5 is sort of close to 12, but it's less than 12 because Jacob had help. Okay, so pause if you need to for as long as you need to, but I'm going to start erasing and I'm going to get up another problem for us. The structure is absolutely the same, but the information we're given is kind of different. So it's going to have a slightly different feel to it. So I'll use my family as an example for this one as well. So in the early days of our marriage, my husband David worked as a roofer. He helped put roofs on. His employer Terry, who had been working as a roofer for a very long time, could, okay, continuing with our lesson on applications involving rational equations. I don't know why the video cut out on me partway through this problem, but here it is. Pause the video if you need to get the rest of this down. We're going to set this up very similarly to the other problem. So we're going to have a percentage for David, and we're going to have, not a percentage so much as a fraction, right? A portion of the job that they did. Working together, they're going to finish one complete job. So what do we know? Well, this time we have information, we have clearer information about what goes on the top of the fraction than on the bottom of the fraction. What we know is that working together, they can roof a house in 4 days. So the amount of time that each individual did in fact work is 4. So the question is, what goes in the denominator of each one of these fractions? How long does it take them working alone? And that's what we're looking for. We don't know that for sure. What we do know is that Terry can work 3 times faster than David, because David's just learning. Terry's been doing this for years and years. This is representing David. This is representing Terry. And here's where there's a little bit of a twist. It can be tricky to know where to put the 3 times, right? So we're going to want somebody working for a certain amount of time and somebody else who takes 3 times as long. And since it says Terry could put a roof on the house 3 times faster than David, you might think that the 3 times might have to go with Terry because he's 3 times faster. But think about it. If you plug in 2 days here and 2 days here, isn't this person working 2 days and that person is working 6 days? David is the one who's slower. It takes him 3 times as long. And that's kind of tricky. People get very confused about this, so be careful with this. You're going to multiply the amount of time that it takes Terry by 3 to get the amount of time that it takes David, because David takes longer. He is slower. At least he was back in the day. So, again, we find an LCD. We multiply both sides by that LCD, and we solve the problem. Distributing here, when you multiply this by the first term, the 3 t's cancel, and we get 4. Multiplying by the second term, just the t's cancel out, and I get 3 times 4, which is 12. That's equal to 3t, and now we just have a linear equation. We need to get the t by itself. 4 plus 12 is 16. Divide both sides by 3, and we get that the amount of time is equal to 16/3. But you know, what is that really? And by the way, have we answered the question? How long would it take each of them working alone? So we need an answer that says Terry takes this long and David takes this long. I want to simplify this a little bit. Our units are days. 3 goes into 16 5 times with 1 left over. That's 5 1/3 days. T is the amount of time it takes Terry, working all by himself, to do the whole job. So Terry can do this in 5 1/3 days, but David, who takes 3 times as long, well, that's easy enough to find. If I multiply this by 3, it's the same as multiplying this by 3, which would just cancel the 3 out. 3 times 5 1/3 days would be 16 days. Wow, that must be a really big house. Okay. We are going to do one other work problem, because sometimes there can be a little twist. Sometimes maybe you don't want to do a whole job. Maybe you're filling a swimming pool and you only want to fill it halfway. Sometimes you're not working together, sometimes you're working against each other. My first problem in the previous video, I could have said, how long does it take for the room to get totally clean or totally messy? If I'm in the room cleaning it, well, one of my sons is in the room messing it up. Well, if you have 2 things working against each other, instead of adding here, you're going to subtract. Again, if you still need to get this information down, pause as long as you need to, and then hit play when you're ready to move on. So here is our final problem, and it does have to do with a swimming pool. So somebody made a mistake. They're trying to fill it, but they left the outlet pipe or the drain open at the same time as they're filling it. So an inlet pipe can completely fill a swimming pool in 9 hours. And an outlet pipe, in other words, a drain, can empty the pool in 12 hours. So somebody made a mistake and left both pipes open. So I'm just going to say if both pipes are open, one filling, one draining, how long will it take to fill the pool halfway to the top? So we're actually only doing half of a job. We're not filling the whole pool. So up here, the thing can empty the pool, the whole pool. This one can fill a swimming pool, but we're asking about halfway. So when we add the fraction, or when we combine, I shouldn't say add, inlet and outlet both working, we want the job that's accomplished to be 1/2 of the full job of filling the pool. But because the outlet is draining while the inlet is filling, these are doing the opposite actions, and so we're going to subtract rather than adding. They're not combining their work, they're working against each other. So we're going to have a fraction for each with a minus sign in the middle. The inlet can fill the pool in 9 hours all by itself. Since that's the amount of time it takes to do a whole job all by itself, the 9 goes on the bottom. The outlet pipe can empty the pool. It can do its whole job all by itself in 12 hours. And again, the minus takes care of the fact that their jobs are exact opposites, one filling, one emptying. The question is, how long will it take them to fill the pool halfway to the top? They have both been left open, and they're left open for the same amount of time. So I'm just going to say T for time, and then we go about solving this rational equation. Rational because it involves fractions. We want to cancel out the 9, the 12, and the 2. And an LCD of 36 will do that for us nicely. Put a 1 on the bottom if it helps. Distribute through. Over here. 36 times t over 9, well, we could cancel with the 9 and the 36 and get a 4 up here. So this is going to be 4t. Then multiplying by the next term, 12 goes into 36 3 times, so we get 3t. Over here, we just have straight up fractions, no variables in there at all. 2 goes into 36 18 times. 4t minus 3t is equal to 18. So that's just 1t, or just t. That's 18. Well, what does that mean? Let's come back over here and look at our units. We are talking about hours in each case, and they're asking us how long will it take to fill the pool halfway. So this is hours. So we could say in 18 hours, the pool will be half full. Hopefully at that point somebody notices that they accidentally left the drain open, and they will close that pipe. So we can ask all sorts of other questions related to this. If somebody closes the pipe after 18 hours, how much longer will it take the inlet pipe to fill the pool? We could have asked a question such as, if the drain had only been open half of the time, then how long would it take for the pool to fill all the way or part of the way? So all of those take little tweaks to what you've got. But hopefully the tweaks make sense, right? If you have two items working against each other, we have minus instead of plus. If you want half of a job to be done, then you use a 1/2 instead of a 1. We saw in the last problem, if someone can do a job 3 times faster, well, one of the people completes the task in 3 times your variable, 3t, and the other person can complete it in just the time of the variable, just t. So these problems can be changed a little bit, but the basic idea is what percent or what fraction of the job did one object or individual do? What fraction of the job did the other object or individual do? And then that's going to be equal usually to 1. But maybe you want to do half of the job sometimes. So I hope this helps you as you do your work with applications involving rational equations.